If you're a human, you've likely heard of pi. It appears in circles, waves, and countless formulas in science. If you've taken calculus, you've likely encountered phi, the golden ratio, which shows up in geometry and art. Or even e, the base of natural logarithms. Yet, there is another mathematical constant that is far less famous, much more subtle, and surprisingly counterintuitive. Now, consider the function f of x is equal to 1 over x. Now let's highlight the points where x is an integer. Then draw rectangles for each height of every blue dot with a base of size 1. Next, consider the area under the curve from 1 to infinity. In other words, the integral from 1 to infinity of 1 over x dx. As we can see, the integral diverges. Consequently, so does the total area of the rectangles as per the integral test for infinite series. Given that, what's the area of the region shaded in green? In order to compute this area, we need to get the area of the rectangles and subtract from it the area under the curve. But we previously said that both areas are equal to infinity for each one diverges. And so we've got infinity minus infinity. But infinity minus infinity is an indefinite form. So is the area indefinite as well? Well, not quite. Instead of plugging in the infinite values of the areas, we should see each area for what it is, and for what each represent. Now I'll go ahead and call the value of this area gamma, and as it's often the case in mathematics, and against our intuition, this turns out to converge to a number. And this is exactly what we were looking for, the Euler-Mascroni constant. And thus, you can add it to your repertoire of mathematical constants.